Hello everyone. In today's session, we will talk about the heat transfer by natural convection. This is one of the experiments which is done in heat transfer lab. In today's session, we will only talk about the theory involved in this experiment, not about the experimental detail. From this experiment, we learn to find the heat transfer coefficient for the natural convection of air for vertical as well as horizontal tubes. We also compare the experimental values to the values calculated using the empirical correlations. We'll discuss these things. First of all, we'll talk about the vertical tube, which is made of metal. Here, heat is transferred from the outer surface of the tube to the surrounding medium. Surrounding medium is air, which is still. That means heat will transfer from the outer surface to the surrounding medium by natural convection, which is originated due to the density difference caused by temperature gradient. The surface of the tube is heated using the steam. So when steam enters, it condensates on the inner surface of the tube. Since here steam is passed continuously, therefore it will come out from the other end, which is open, and the condensate is collected in a container for a specific period of time, which mass is measured using weighing balance, or mass also can be measured using the volume. First we need to measure the volume of this condensate, which is water, and since we know the density, therefore multiply the volume by density, we can know the mass of the condensate. So what is happening here? Steam is entering, it condensates, therefore steam will lose its latent heat. The outer surface temperature is measured using the thermocouples. There are several thermocouples. Here, six thermocouples are attached at the outer surface of the tube. 1, 2, 3, 4, 5, and 6. Therefore, we will have average temperature of the outer surface that we can find. Say this is Ts. Ts is the average surface temperature. Say Ts. So that will be T1 plus T2, T3, T4, T5, T6 divided by 6. T infinity is the surrounding medium temperature, which is air. Now we'll find the heat lost by the steam, latent heat, in the condensation process. So that will be the latent heat of the steam, or we can say that latent heat of vaporization of water. Both are same. Either we can say latent heat of steam or latent heat of vaporization of water. Latent heat of steam. Say this is lambda, and unit is kilojoule per kilogram. Kilojoule per kilogram. Now heat lost we can find latent heat Q. Total heat lost by steam or heat released during the condensation for a specific period of time T. So mass is M, that we have measured this collected mass, and lambda, this one. So this is the heat transfer, and we can find the heat transfer rate m dot lambda m by T into lambda, the collected mass for a specific period of time, that is T. For example, we have collected the mass for 15 minutes, therefore time will be 15 minutes. Next, we know that the heat transfer rate in this direction will be constant. So heat transfer rate from the outer surface to the surrounding, we can find Q dot is equal to HA, heat transfer coefficient, surface area, heat transfer surface area, and delta T. Delta T means Ts minus T infinite. T infinite is also measured using thermocouple. This is also measured using thermocouple. So both can be equated. From here we can find heat transfer coefficient. Area is surface area pi d into length. Length is h. This is, I'll write small h. Pi dh. D is the diameter of the tube. So all values we know, therefore we can find heat transfer coefficient from the experiment. Now we will compare this value to the theoretical value. For natural convection, we have a correlation between Nusselt number, Prandtl number and Grashof number. This is known as the Rayleigh number. The product of Grashof number and Prandtl number is known as Rayleigh number. And this correlation is applicable when Rayleigh number is between 10 to the power 4 to 10 to the power 9. So first we need to calculate Grashof number, Prandtl number, and then product of these two should be in this range. This range is applicable for laminar flow. If we have a turbulent flow, then we have a different correlation, little bit different, not much. 1 by 3. Here power is 1 by 4. And for this, Rayleigh number lies 10 to the power 9 to 10 to the power 12. This is for turbulent, this is for laminar. This is for laminar. And this is for turbulent. So first of all, we have to calculate Rayleigh number. Once we find the range, we can apply the particular equation, either this one or this one. Let's see what is Grashof number and what is Prandtl number. First we'll see Grashof number, GR. Grashof number. Grashof number compares two forces. One is that buoyancy force and other one is that viscous force. So this is the ratio of buoyancy force to the viscous force, and I'll write the formula of this: beta G delta T. Delta T means temperature difference between surface and surrounding. Ts minus T infinite LC cube divided by nu square. Here beta is the volumetric expansion coefficient. For the ideal gas, this is just the inverse of the temperature. Temperature of the film. Temperature of the film TF. G is the gravity 9.81 meter per second square. LC is the characteristic length. In this case, LC is the H. LC is H. In the vertical case, it is H. And nu is the kinematic viscosity. Prandtl number, it is written like Cp mu by K. Specific heat capacity of the fluid, viscosity of the fluid, conductivity of the fluid. Here we need to change the symbol for the length of the tube, because same symbol we have used for the heat transfer coefficient. Better we can use small l. So LC means here length of the pipe. All the fluid properties, for example Cp, mu, K, beta, nu, should be considered at the film temperature. What is the film temperature? TF. We can draw the profile. In case of vertical plate or cylinder, we see the profile like this way. I am not going in detail. So thickness of the boundary layer increases when we go up, and outside temperature is T infinite everywhere, surface temperature is Ts. So here film temperature is approximated by taking the mean of the surface temperature and surrounding temperature. Tf means Ts plus T infinite by 2. At this temperature, all the fluid properties should be considered. Remember that. Assume that our Rayleigh number lies in this range, so we can use this expression and we can find the heat transfer coefficient, because NU is nothing but the ratio of convective heat transfer to conductive heat transfer of the fluid. This is H LC by K, not HD, LC, and LC is L, so length of the pipe, because this is vertical. Here buoyancy effect is working along the axis of the tube. GR and PR both are found from these expressions. This one, this one. All the fluid properties are considered at the film temperature, which is the average of surface and surrounding temperature. So we can compare this theoretical value to the experimental value. One thing I would like to mention is that the latent heat of steam, which can be found from the steam table, if it is sent at the 100 degree, then lambda will be around 2260 kilojoule per kilogram. Other thing which is very important I would like to mention is that heating is provided using heating coil rather than steam. So if in our setup heater is employed, then we can easily calculate the rate of heat transfer, heat input. Inside that heater is there, and here we will have a board, voltage indicator, temperature indicator, and ampere. For example, we are using such kind of setup. So in that case, we can find the heat input from here, Q, rate of heat transfer. That will be VI, voltage and current. So same approach will be there. VI can be equated now to the HA delta T, Ts minus T infinite. In the case of steam, we were taking latent heat. Now we are taking voltage and current. Theoretical part will remain same. Only in experiment there will be slight variation in the calculation. Now we'll do the calculation for the horizontal tube. Tube is horizontal. Thermocouples are there. Surrounding temperature T infinite. This is the setup where steam is passed rather than heating coil. So same, we know the mass, time, rate of heat transfer, Q dot. That will be M by T, rate of mass transfer into lambda. Experimental approach will remain same. Only theoretical part will be slightly different. In case in our setup heating coil is there, then we can use VI. In case of steam, this one. In case of heating coil, this one, we can use steam. Heating provided by steam, heating provided by heater or heating coil. Then we can find the heat transfer coefficient, HA, Ts minus T infinite. Ts is the average of all the temperatures, surface temperatures. Area will be pi d L. Suppose this is the L, diameter d, so area will be pi d L. So from here we can find H. This is the experimental approach. Q dot by A Ts minus T infinite. Q dot means either this one if we never set up steam is there, otherwise this one if we never set up heating is provided by heater. Now coming to the theoretical study, this one. So now Grasp number will be this time beta G Ts minus T infinite LC divided by nu square. Here LC this time will be D, not L but D, diameter of the tube, because buoyancy effect is working in this case in the normal to the axis of the tube. Prandtl number will remain same, Cp mu by K. Nusselt number will be changing. Now this time we will have to take H d by K, not L but d by K. This one we will have to take. And all the fluid properties should be considered at the film temperature. And film temperature is nothing but Tf, which is the average of surface temperature plus surrounding temperature. This one. And beta is nothing but 1 by Tf. Beta is equal to 1 by Tf. And all the fluid properties such as K, Cp, mu, nu, beta should be considered at this temperature. Now we'll write the empirical equation in the case of horizontal cylinder. So that will be Nusselt number is equal to 0.53 Grasp number, Prandtl number 1 by 4. This is for laminar region. Laminar region 10 to the power 4 to 10 to the power 9. So first of all, just calculate the Grasp number using this expression, Prandtl number using this expression. Then product of these two should be in this range if we have to use this one. Otherwise, if it is in turbulent region, then we have a different expression, that is 0.13 gr into pr 1 by 3. This time Rayleigh number is 10 to the power 9 to 10 to the power 12. This is for laminar and this is for turbulent. Nu should be considered Hd by K, and while calculating Grasp number, Lc should be considered D. So D cube will be there, not L cube. Otherwise, rest of the things will be same. The expression is slightly different compared to the vertical one. Apart from these correlations, we have one very popular correlation that we can use, and which is known as Churchill and Chu correlation. That one is very popular, and that works actually for a wide range of Rayleigh number. That expression is little complicated but can be used. This Churchill and Chu expression you can see on the screen, this one. So these were few important steps involved in heat transfer by natural convection experiment which we discussed. I'll stop myself and we will see in some other session. Till then, bye bye and thanks for the attention.